Questions about anything from last time? About anything? Well, today I'm going to talk about section 2.2 in chapter 2, which is the title of that is the absolute value and the real number line. But this section has mostly to do with three concepts about the real numbers, namely the order, the distance function, and the topology on R. We'll say more about topology later, but this is the beginning of the subject and the thing I'll touch on at the end. So the real numbers are fantastic in that they're well ordered. So R is well ordered. Which means you give me two real numbers that are not equal. R1 unequal to R2. There's only two possibilities. Either R1 is less than R2 or R2 is less than R1. And, of course, not both. And that follows, you can deduce that from the trichotomy business from last time. The trichotomy principle. Anyway, it's possible to come up with sets that have an order, but they're not well ordered. For the standard example in a book would be a tree. So, example of something that's not well ordered, it's partially ordered. Think of a tree. So it has a trunk, and then some branches, more branches, etc. And you know which way is up. So if I had here's a B and here's an A. Oops, I want to go farther down. Here's an A. All right, if you climb up the tree to get to B, then A is less than B. Okay, let's call this B1 now. If I climb up the tree to get to this B, this A is less than that B2. But there's no relationship between B1 and B2. So sort of the transitive properties of order break down. I mean, that's certainly not well ordered. It's called partially ordered. So I guess that A is less than B1, A is less than B2, but B1 and B2 are not related. If you set up a partial order, meaning climb up the tree to just decide what A less than B means. Okay, so that's not well ordered. It's partially ordered. There's a word for that. Partially. Okay. But today's let's see. Today's subject is the absolute value of a real number. And I like to think of the absolute value function as kind of a distance function in the real line. So I think the distance between two real numbers, R1, R2, well, in my picture above, R1 was smaller, so that distance would be R2 minus R1. But if the other one was bigger, then I'd have to take minus that. So this is a moment when the absolute value comes in handy. So the absolute value function is the distance function on the real line. Of course, let's see, I'm going to be formal for a little bit here. The definition of the absolute value is that the absolute value of a real number is equal to A when A is positive. It's equal to 0 when A is equal to 0. And let's see, if A is negative, then to make it positive, I would take minus A there. Probably learned that in junior high someplace. Okay. Well, we're trying to understand real analysis from first principles. So naturally, there's going to be some formal proofs to begin with. And it's important to read the book carefully and understand those proofs. Yeah, question?
So why is it negative A?
Well, when A is negative, we want something that's sort of distance from A to 0. And so if A is negative, then minus A would be positive, and that would be exactly that distance. So yeah, that's kind of the way I like to think about this thing. Distance from A to 0 would be equal to minus A in that case. So my thinking is in terms of distance from the beginning. Anyway, there's some simple facts that you see right away. Trivial things like, I won't call them trivial, you got to check them. So AB, the absolute value of A times B is the absolute value of A times the absolute value of B. Of course, I'd have to, if I was going to demonstrate that, I'd have to sit down and go through cases. And it'd be kind of excruciating to watch me do that. It's not so excruciating to read it. So I want you to read the book carefully. And let's see, because of that, the modulus, I'm teaching complex analysis this semester too, and in complex analysis, that thing is called the modulus of a complex number. I'll try not to slip up and say that. It's the absolute value. Let's see, the absolute value of A squared would be the absolute, that would be the absolute value of A times the absolute value of A, which is, of course, the absolute value of A squared. But you think about the two cases, if A is positive, that would be A squared. In the case 0, it would be 0. In the case when A is negative, it would be minus A squared, which is A squared. So in all three cases, this is a remark here. This is me thinking out loud. This is equal to A squared. Let's say 0 squared when it's 0. When I go through the cases. Okay, and the book, of course, does that very carefully and goes if-then reasoning. You should read it. Oh, was that number 2? Number 3 is maybe slightly more interesting. If C is bigger than or equal to 0, if C is bigger than 0, then the absolute value of A is less than or equal to C if and only if minus C is less than or equal to A is less than or equal to C. Of course, I like to think about that in terms of pictures. So here's 0, here's minus C, here's plus C, and then the absolute value of C is the absolute value of A is less than or equal to C just means it's in that closed interval from minus C to A. So A would be somewhere in here. That's the picture. And of course, the book writes out a careful demonstration of that I want you to read. Whenever there's an if and only if, you would have to assume this left-hand side. So I assume that C is positive. Then, to show this next thing, something if and only if something, you would assume this side and then show that the other side holds. And then you would assume this other side and show that the left-hand side holds. Okay, so obviously it's going to take some sentences. And it's the kind of thing you have to sit through and do at least once on these elementary facts. And reading a book, let me mention something that's typical in the book. Before I do that, this kind of thing is also similar to a set in set notation. Let's see, we'd have the A such that A is less than or equal to C in absolute value is equal to, well, we have a symbol for this thing. It's the closed interval from minus C to plus C, including the endpoints. Okay? When you want to show that two sets are equal, it's very much like the if and only if thing. You want to show if something is in the left-hand side, then it's also in the right-hand side. That would show as a subset. And to get equality, you got to do the subset the other way. So you start with something in the right-hand side and have to show it's in the left-hand side. Okay? And because these pictures are kind of obvious to look at, it seems silly to do that kind of thing. But it's good practice, and you'll have some homework where you kind of have to do that. Just so that it makes it easier to read the book. So I want you to read the book carefully. Don't skip anything. And the book will sometimes do something like this. So an example, in the proof of number 3 above, here's what the book says. If the absolute value is less than or equal to C, then we have both, here's the word, we have both that A is less than or equal to C and minus A is less than or equal to C. And then the book does this. Puts in parentheses Y. It means think about it. They're skipping something when they say that. You've got to think about it and convince yourself it's true. So don't skip the Y part. Oh, let's see. How do you see that? If the absolute value of A is less than or equal to C, then we have both those things. So you have to convince yourself why, you'd have to go through cases. Case A. Why don't I do two cases at once? If A is bigger than or equal to 0, then of course we would have absolute value of A is less than or equal to C. That's the assumption. And this would be equal to A. So we have the first one. The first one's done. A less than or equal to C is one of the things we have to see, but I have to see the other one. And the other one would be minus A. Well, if A is positive, then this would be less than or equal to 0. And of course, 0 is less than or equal to c. So check. In that case, we have both of them. And of course, the case a less than 0. I won't do it again. So we have two cases to consider. Similar. Convince yourself that you can do the same thing when a is negative and get both of those things. See, questions about that? It takes some discipline, but it'll pay off. It'll help you solve problems. I guess I should have done more examples maybe, because I've had some people in my office asking me what the heck they're supposed to do. Let's see. A baby fact from last time that kind of feels like it should have been an axiom is that minus 1 times a real number is equal to the additive inverse. Okay, I didn't write any proofs of facts like that because I wanted you to experience them. But it's the kind of thing we showed that let's see, 0 is equal to 0 times a. That was one of those things that followed from the axioms in like a very one-line demonstration from the axioms. And 0 is equal to 1 plus minus 1. Okay. And there's a distributive law of multiplication. And so 1 plus 1 minus 1 times a is 1 times a plus minus 1 times a. And 1 times a is equal to a. And so I see that a plus minus 1 times a is 0. And that means that this is the additive inverse. So the aha moment is minus 1 times a is the additive inverse of a. Okay? If somebody asked you to demonstrate this fact, there's multiple ways to do it. This was my way of thinking of how to do it. And the book gives you one way of doing these things. So in the homework, for example, you have to show that minus a times minus b is a times b. It's the kind of thing you need to sit down and do carefully at least once in your life, and then be done with it. I'm not trying to torture you. It's just a good thing to learn how to do. Questions about any of that? So I'm going to skip some of these really piddly little things. You need to read them, but I want to do the biggies. And one of the biggies today is the triangle inequality, because it has a lot to do with distance and topology. Triangle is a thing, is a geometric thing. So, the triangle inequality. I'm going to demonstrate it today. It's fairly straightforward. It's the absolute value of a plus b is less than or equal to the absolute a plus the absolute b. That's true for complex numbers too, with the modulus. You probably learned somewhere. And let's see why that's the case. I can do kind of a sneaky little quick proof. Let's see. That number 3 above told us that minus absolute a is less than or equal to a is less than or equal to plus a. absolute A. That follows from number 3. Above. Okay. Similarly for B, minus absolute B is less than or equal to B is less than or equal to that. If I was going to prove these things, I would check them for positive, 0, and negative and say, sure enough, those are true. If I hadn't already done B, number 3 above. Okay, so the next thing you do is add these things together. So I'll add them together. If those inequalities hold, then when you add them together, these inequalities would hold. Minus A minus B is less than or equal to A plus B is less than or equal to absolute A plus absolute B. And of course this side is minus absolute A plus absolute B. And those three inequalities by number 3 implies that the absolute value of A plus B squeezed in by those two things, plus and minus those two things, that's the that absolute value is less than or equal to. So I'm using 3 again. So let's see, what does that show? That shows that the absolute of A plus B is less than or equal to absolute A plus absolute B. Check. And that's from 3 again. So the triangle, if this was complex analysis, I'd have to spend a couple more minutes demonstrating the triangle inequality. But in the real case, it's sort of ho-hum and straightforward. But whenever you have a triangle inequality, there's another thing that pops out instantly from it. Questions about triangle inequality? A consequence of the triangle inequality sometimes it's great to have a less than or equal to inequality, especially when something's in the numerator. But when something's in the denominator, you would rather have a bigger than or equal to inequality. And I'll get more particular about that in a second. But let's see. A plus B, so it's greater than or equal. So it's the other direction inequality than the triangle inequality. It's greater than the absolute value of A minus the absolute value of B, absolute value. Okay. This is particularly useful when that thing is in the denominator. A plus B is a denominator. As we'll see throughout the course. Okay, and because this thing is so important and useful, I'm going to demonstrate it here. Let's see, by the way, I can replace B by minus B in that inequality. When we do that, we see A minus B is also greater than or equal to A minus. So when I put the absolute value of minus B, that would be the same as the absolute value of B. Okay, so that's another version of the same inequality. Well, let me demonstrate why this is true. Oh, let's see. It's kind of a tricky little thing to mess around with, but it's not hard. I can write A is equal to A minus B plus B. And so the modulus of A would be equal to the modulus of that right-hand stuff. And when I do the triangle inequality, I'd have that's less than or equal to A minus B plus modulus. Am I saying modulus? I'm really sorry about that. I usually teach complex, not real. 25. I'm teaching also this semester. Okay, well, that doesn't look like what I want. It kind of looks like a piece of what I want. This would give me A minus absolute A minus absolute B is less than or equal to absolute A minus B. Okay, that's kind of half of what I want. Now I'm going to do B equals B minus A plus A and do the same thing and get that B is less than or equal to absolute value B minus A plus absolute value of A. And of course, the absolute value of B minus A is the same as the absolute value of A minus B. So I get absolute B minus absolute A is less than or equal to A minus B. Okay, let's call this star number 1 and this star number 2. Those two starred inequalities give me exactly what I need. Let's see. The book would maybe do something slightly more formal than I feel like doing right here. I like to do something involving cases. So let's see. We could do one thing. I'm going to do something different. I'm going to do the cases B bigger than A. Absolute B bigger than absolute A. Then I would have, star 1 would give me what I want. Would say that A minus B is bigger than or equal to A. What? No, that's not the one I want. It's star 2, the one that's going to give me something I want. Star 2 tells me that A minus B absolute value is bigger than or equal to B minus A. And because B is bigger than A, this is equal to the absolute value of B minus A. So check. Then there would be a case of absolute B equals absolute A. And then you ask yourself, is A minus B bigger than or equal to 0, which is this would be 0. So it would be one of those, duh, yeah, check. That's the dumb case. And finally, the last case would be case A. I guess I want to make them look mutually exclusive, which they are. Then it would be B less than A. And then I'd use star 1. Which was, let's see, it would tell me that A minus B is bigger than or equal to A minus B, and A is the big one this time. So that would be positive. That's a positive thing. Oops, sorry, what did I do? What? Never did that before. Sorry. This thing right here would be positive, and so it would be equal to its absolute value. So check. Questions about that? That's the way I like to do it. Eventually we're going to talk about differentiability of functions from a deep level, foundational level. And so, we've learned in freshman calculus how to graph the absolute value function. It looks like this. When x is positive, it's x equal x. That would be y equals x. When x is negative, it would be y equals minus x. And of course, it's 0 at 0. And so it's a classic example of a continuous function, and it's not differentiable at the corner. It's got a kink there. The slope is plus 1 to the right and minus 1 to the left, and of course there's no slope at the kink. And another graph, once you know that graph, you can shift it easily and get a graph like this. Make that be A. This would be the absolute value of x minus A. The kink would be at the A. Well, I like to think of the triangle inequality as a numerator estimate. So it would be A plus B is less than or equal to absolute A plus absolute B is a numerator estimate. And I like to think of the other one of A plus B is greater than or equal to the absolute value of A minus absolute value of B is a denominator estimate. So if I was estimating A plus B over C plus D, which is something we quite often have to do, I would use the numerator estimate in the numerator, and I'd use the denominator estimate in the denominator. And hopefully that would allow me to get an upper bound for the thing on the left. Okay. Similarly, it's useful when we're doing things like this. When estimating an f of x over a g of x. You want to know that the numerator estimate, we'd estimate that that's less than or equal to the maximum of f, absolute f. And the g, you got to make sure it doesn't get anywhere near 0. And so you could estimate that by seeing what the minimum of g is. Okay, and you'll have some homework problems where, kind of like calculus problems or pre-calculus problems, where you're looking for the max of a numerator and the min of a denominator. And usually it's just, you can either graph it and look at it and figure out what it is, or you can use inequalities. Anything you can see in a graph, you can demonstrate using inequalities. In the beginning, you need to demonstrate them using formal reasoning. Okay. I promised I would mention the word topology today. The beginning of topology is deciding what your open sets are going to be. And there's something called a basic open set in the real line. so the start of topology, an epsilon neighborhood of A. Epsilon is going to be a small positive number of a point A. I like to think of that as a disk because I like to be in the complex plane. But when we're in the real line, it's an interval, and the book calls it V sub epsilon. I would be inclined to call it D sub epsilon for a disk, because it's when you think in terms of distances, it's going to be all the points that are a distance epsilon or less from A. So it's like a disk of radius epsilon. That's the way I like to think about it. Okay, so that's going to be the set of X such that the distance from X to A is less than epsilon. Okay, and my feeling about that is if I was in the complex plane, I would take a disk of radius epsilon, and here's A. This would be a radius epsilon. And that would give me these points along the real line, like that. But it wouldn't include the points on the circle. So a standard way to write that. So I guess it's a remark. This would be the disk of radius epsilon about A in the complex plane in Math 425. And that's why I like to think of this V as a D, a disk. So let's see, when I don't cheat and go into the complex plane, it's standard to write this set like this. So here's an A. This set is, they make little parentheses like this. This point is A minus epsilon, and this point is A plus epsilon. And you make that more like a parentheses. Okay, and the set is this stuff between those parentheses, not including the endpoints. That's what those parentheses mean. If I wanted to include the endpoints, maybe I'd make square brackets there. Well, there's this theorem that the book does right away here. If X is in a little epsilon neighborhood of A for all epsilon, when I say all epsilon, I'm thinking no matter how small. Well, think about that. If I shrink that interval down, if X is in the yellow stuff there, and I start shrinking those edges down, I could squeeze X out, and X wouldn't be in. I could find an epsilon that's small enough, and I could squeeze X out. And so the only way this could be true for all epsilon is if X is equal to A. Okay, well, this is the kind of thing that Richard Dedekind would have said, oh, I better prove this from first principles. And of course, the book does that. Read the one in the book. It uses a lemma from a previous time. It's basically the lemma that there's a no smallest. So the book, a lemma, there is no smallest positive real number. So you can write out a formal proof that's a two-line thing, and it's very easy. But I like to have a more tactile proof, which is okay. There's always more than one way to demonstrate something. But here's an alternate proof. Suppose we have the assumption. Suppose the hype, namely that x is in the little neighborhood for all epsilon, and assume x is not equal to a. Then, of course, the modulus of x minus a is unequal to 0. Call it c. And then it's clear that if you take epsilon less than c, so the oops would be if epsilon is smaller, if 0 is less than epsilon is less than c, then x is not in the epsilon neighborhood. And that's contrary to our hype. So my assumption was wrong. X has to be equal to a. Okay, that's enough of that. Question?
Yeah, can we just set epsilon equals c and on like the border?
Oh, that's true. That would be the first epsilon that violates that. But there's always a smaller epsilon. So that it's very related to the fact that there's no smallest positive real number. If c were the smallest positive real number, I'd be sunk right now. Yeah. I want to talk about something more fun this last couple minutes. So next time is very important. It's because we're going to do next time. We're going to talk about the least upper bound principle. Which is related to the, I'll say comma, greatest lower bound principle. So the least upper bound principle was called the LUB principle, and the greatest lower bound principle is called the GLB. Okay, I would call these deep facts about the real numbers, and so they're very foundational facts. They're these two facts. Actually, one implies the other. So my favorite is the LUB principle. They're equivalent. But it's the basis of why calculus works. So I would call it a deep fact. Of course, Richard Dedekind was obsessed with it. It's why calculus works. And you didn't think about it when you took calculus because you didn't care why it worked. You just wanted to see how it worked and have a feeling for how it works. You can get a lot of feelings before you have to start thinking this deeply. Because you can make mistakes if you don't understand what you're talking about. And of course, the founders of the subject made mistakes every now and then because they were being too loose with what they were doing. So let me in the last few minutes here, give you a feeling for what I'm talking about. One of my heroes is Dedekind. And I told you about Dedekind cuts last time. So, for example, for the square root of 2, Dedekind partitioned the rational numbers into things to the left of the square root of 2. Let's see. Maybe I should make these different colors. This would be 0 over here. These q's that are positive are the q, which are rational numbers, such that q squared is less than 2. Okay? There's gobs of them. They're dense. They're not everything, but they're dense. For example, we know that square root of 2 is not a rational number. Okay, and then these are just the rational numbers that are less than 0. That partitions the rational numbers into a left side and a right-hand side. And Dedekind called that well, he didn't call it a Dedekind cut. He called it a Schnitt. And he defined that to be the square root of 2. All right? Square root of 2 is the least upper bound of that set. There's lots of upper bounds. Here's an upper bound for that set. It's bigger than everything in that set, so it's an upper bound. By the way, everything in the left-hand side, q's, is less than anything on the right-hand side, q's. So this partitions the q's into a smaller side and a bigger side. And that's why the order properties were important in the foundations here. Okay, that's an upper bound. And I can slide that upper bound until I can slide it right down to the square root of 2. This is a least upper bound. And I can't slide it any further. As soon as if I slide it just a little tiny bit more, then there's going to be purple lines between where I get it and the square root of 2. So it's not an upper bound anymore. All right? That's a least upper bound. And let's say that's a square root of 2. What if I did the same thing for square root of 2 is 1.4. 2. If I do the same thing, but then I'd have a lot of q's here. I'm not taking q's squared to be... Two is rational. So when I do the partition, 2 would be in there. And so I'm making a dot there. This would, I can do the same thing. There's upper bounds here that are clearly above that whole thing. But this is still my least upper bound. It's an upper bound. It's bigger than or equal to everything. And this 2 is also a least upper bound, even though it's in. Still called the least upper bound. And the reason is that an upper bound means that m is bigger than or equal to everything in the set.